Hi friends, my name is Chetan Kumar. I'm working as a physical design engineer in Optometra Consultancy. Today I'm going to talk about how the IC is made. So, uh, all the chips starts with a very simple raw material that is sand. It's primarily made up of silicon dioxide or silica. So, it's only even found as a compound with oxygen. Complex chemical and physical process are required to ensure that silicon crystals meets the high production standards that apply to chips. To convert silica sand to silicon, the sand is combined with carbon and heated to an extremely high temperature to remove oxygen. A number of other finished products are required to create the finished product, namely an extremely pure monocrystalline silicon ingot is called a bull with only one impurity atom for every 10 million silicon atoms. So silicon bulls are fabricated in a range of different diameters. The most common sizes are 150, 200, and 300 millimeters. Wafers with large diameters offers more space for chips, and extremely thin wafers then cut into small silicon balls using special sawing technique. These wafers are basic building blocks for the subsequent chip production. So, silicon is the semiconductor device. This means it can also conduct electricity and also acts as an insulator. Its atomic structure looks like this. This is the atomic structure of silicon, and you can see that there is no free electrons in the outer shell. As a result, this is a pure monocrystalline silicon is non-conductive at room temperature. To allow it to become conductive, small quantities of specific atoms are added as impurities to the wafer. So these impurity atoms must have a number of outer electrons, which it's either one more or one less than the silicon. We can see that silicon is in 14th group of the elements table. So the 13th and the 14th 13th and the 15th groups have to be used in this process referred to as doping. So boron and the phosphorus is very suitable elements in these groups. These are very close to the silicon on the periodic table and therefore having similar properties. Phosphorus has 5 electrons in the outer shell and therefore have so we when we add this to the silicon as doping, the fifth electron is free. So this means that silicon phosphorus crystal is n-conductive. So here we can see that the fifth atom, four electrons are combined with the silicon atom electrons. One is free. In the case of boron, we have only three electrons in the outer shell. So it means that uh, when we add this to the silicon crystalline, it should be like the one electron in the silicon atom is free. So this creates an electron hole. The hole moves through the crystal. like positively charged particle, making the material p conductive. So transistors are built on the p and n conductive layers that exist in a doped vapor. Transistors are the smallest control unit in the microchip. Their job is to control electric voltage and current, and they are by far the most important components of electronic circuit. Every transistor on a chip contains a P and N conductive layer made up of silicon crystals. They also have a additional. So here you can see that silicon dioxide, which acts as an insulator, a layer of electronically conduct polysilicon, is applied on a top of this. Every transistor has three terminals. This is the gate terminal. This will change according to how which substance is this. So the two other terminals are source and drain. So when we apply the voltage to the other two terminals, the current won't flow because there is no channel to flow. So uh, what we do is let's apply the charge to the middle terminal. So this middle terminal is positive, so it will attract the negatively charged particles towards it. So these electrons are moving towards the gate. So this will form and channel underneath the gate. So here these electrons are accumulated beneath the gate and forms a channel through to the other terminals. So when we now the current formed underneath the gate, electron flow through this channel. Electric circuit is, because the electric circuit is closed. In this way, transistors can be turned on or off, or 0 or 1. So here there is no flow of current. So this is off state and this is on state. Here you can see that. So now let's see how these layers of are created on this wafer. So first step is let's take a substrate. Here we'll take a P substrate. So next step is oxidation. We'll expose this substrate to the high purity oxygen and hydrogen at approximately 1000 degrees Celsius in oxidation furnace. Step three is photoresist coating. So first we had a, silicon dioxide coating, and upon that we are having photoresist coating. So photoresist is a light sensitive organic polymer, softens when exposed to light. So this layer, when it exposes to the light, this will get softened. So this is a masking process. Here you can say that this is a mask and the light won't pass through it. But here, this is the in this portion the light will pass through it, and this portion is softened. Later, that portion is removed with the help of acidic or basic solution. So SiO2 is selectively removed from areas of wafer that are not covered by the photoresist by using hydrofluoric acid. So where there was no photoresist, we'll remove the silicon dioxide wafer too using hydrofluoric acid. So now we strip off the remaining photoresist layers, and in this step we'll form a N well. N well is formed with a ion implantation. So after the N well is formed, we'll rip off the oxide layer using hydrofluoric acid. In this step, again the polysilicon is layer is added using chemical vapor deposition. So here you can see that the polysilicon layer is added, and then there is a masking process, and these are the connections for the gate, and the rest of the layer is etched off. So N diffusion, here in this case, N diffusion is formed. It forms NMOS source, drain, and N well contacts. So here you can see that source, drain, and N well contacts. So in this step, the dopants were diffused. Here you can see that N plus ion implantation. Again, we'll strip off the oxide layers. Similarly, the steps from P plus diffusion regions for the PMOS source and drain and substrate connections. That so the devices are to be wired together. Cover chip with thick field oxide. So this is oxide layer. Edge oxide where contact cuts are needed. So here we can see that this in this portion we need contact cuts. So wherever the cuts are needed, the oxide is etched off. So here you are placing an aluminium over the whole wafer. So this will be for the contacts from the outside to the inside chip. So wherever the contacts are needed, there the metal aluminum is kept, and the other places it is taken off. So the PWell here we used NWell process. PWell process is similar to the NWell process, except that the PWell acts as a substrate for the end devices within the parent end substrate. So advantages of NWell process: NWell CMOS are superior to PWell because of lower substrate bias effect on transistor threshold voltage and lower parasitic capacitances associated with source and drain region. Latch-up problems can be considerably reduced by using a low resistivity epitaxial P-type substrate. Uh, but annual process degrades the performance of poorly performing P-type transistors. Thank you.